general relativity step by step. I think I forgot a minus sign there, and this one here should be a sigma. That's the summation variable. These equations here, and I think I may have forgotten. Look, I've opened lots of brackets and not closed them. I think I should have closed that bracket there as well. There we go. These equations here look quite fearsome, but they're not as bad as they think, because they're not as bad as they look. We're going to make a few simplifications. I mean, what I'm going to do is look for things like this. If I have di g alpha beta by di x gamma di, oops, that's a delta, di x alpha beta gamma delta, then that equals di g alpha beta if I differentiate it the other way around, delta and di x gamma, because I've got regularity conditions which I'm kind of assuming and not stating very clearly, but I'm going to assume things like this. And of course I can also use the fact that g alpha beta, g beta delta is the Christoffel symbol. I've got a delta as a subscript as well. Is the identity matrix. So I'm going to use these. I'm going to use these facts here. Okay, so what do we do with this great big mess? Well, the first thing is to spot. Well, I guess you could do it in any order. Is to spot pairs like this, where we're changing the order of the differentiation. And so this term and this term, they're the same term, except that we've got di by dx mu and nu, and here we've got nu first and then mu, and it's one minus the other. So I can just cancel those out, which I will do in green. There you go. So instead of 6 terms, we've only got 4 terms to deal with. Now I'm going to use this relationship. Oops, I'm still in green. I'm going to use that relationship there to simplify it a little bit more. So let's just have a look at this. We've got a half. I'll put the half there, I guess, times. Now what have I got here? I've got Now I'm stumbling a little bit. I'm stumbling a little bit because I'm forgetting my own restriction that this is to be evaluated in local inertial frames. So this thing here is a constant because I can just choose it to be what I want, and I want it to be that, which is constant. So it moves past the differentiation. In fact, not there, never mind there, I can stick it here. And now I can use this cancellation property because I'm summing there and there, that pi index there. So we've got a delta term, a Kronecker delta, alpha and sigma. Let's just write that in and see what happens. I'll do the first one. Di x mu of g alpha pi g pi sigma from here. And then this term's gone, so we're getting there. And you see, look, this will cancel out using this relationship here. So we're getting there. Di g nu sigma by di x beta minus di g nu beta by di x sigma minus di by di x nu of g alpha pi g pi sigma. See, technically I'm committing a bit of a sin here because I'm using the same variable here as here, but it doesn't matter. I can use any symbol. I can use a little star. In fact, I will. I'm just going to put a star there. There you go. Star. There you go. Deal with it. Now, what have I got left? I've got this term here and that term there. So I've got di g mu sigma minus di x beta minus di g beta mu by di x sigma. There it is. And I'm going to have to be a little bit more careful about closing the brackets. There's one, there's another one, and there's the big one outside the half. I want you to see how I'm not scared of this formula. I'm looking at it and I'm thinking, well, what do I know? You might say, oh, look, I can get rid of that because that's equal to 0. Well, yes, it is, but the differential of it isn't equal to 0. So what you've got to do is have this back and forth switching between mathematics and physics. Let's just do things slowly, one step at a time. Let's see if I can zoom in a little bit more here. We've got a half of di x mu, and then I'm going to replace that with just a delta term, alpha there downstairs, sigma upstairs, and then we've got di g mu sigma by di x beta minus di g from here, that's not very good, g mu beta by di x sigma, minus the other term, di by di x nu, which is here, delta, oh that should be all in brackets, but you'll see, now we can make other simplifications. What have we got left? That star thing cancelled, remember I wrote the pi, rewrote the pi as a sigma is here, di g mu sigma by di x beta, minus di g beta mu by di x sigma. The other thing I want you to observe is that I'm doing it one step at a time. Equals a half of, did I close all those brackets? Yeah. Di x mu. See, all I'm doing is evaluating that term there. This one here states that alpha must be equal to sigma, and if it isn't, well, I can bin it. And I'll just check. I'm summing over delta, which is upstairs. Sorry, I'm summing over sigma, I'm sorry. Sigma is upstairs here and downstairs here. That's cool. Upstairs here, and that counts as downstairs. So it's a correct tensor equation. So what I'm going to do is take this stuff in the bracket here and just rewrite sigma as alpha, because I know that alpha equals sigma from here. That's just a Kronecker delta. Di g mu, and then I'm rewriting sigma as alpha by di x beta, minus di g mu beta by di x. That sigma is contracted with that sigma, which must be equal to alpha. Still a bit of a mess, isn't it? Minus di by di x nu times, and we can play the same trick again. We're going to contract on sigma, which is there and there, so it's di g mu alpha by di x beta minus di g beta mu by di x alpha again. Now, does anything else cancel? I'm pretty sure it doesn't, because I'm pretty sure the term has got four equations. The expression I'm looking for has got four equations, but it doesn't hurt to check. Can I find anywhere that sums? I don't think I can, because that mu, it's a mu on the top, and here it's a mu on the top. So we've got a di by di x mu of a mu term, and di of x mu with a mu term. I don't think these are going to cancel out. Well, they don't, in general. Equals 1/2 of di 2g mu alpha, which is that term there, by di x mu di x beta. There's no summation in that at all. I've used all the summation. This is what's happening. There's no summation here. There's no summation in this. Well, let me write let me write the next term anyway. Di 2g, that's this one here. I'm doing mu beta by di x mu di x alpha. Minus di 2g, and this one mu alpha by di x mu di x beta, plus, because minus and minus is a plus, di 2g beta mu by di x mu, what's that one? That's an alpha. There's no summation in any of this. There's no repeated indices, so that should be a square bracket, I guess. There's no repeated indices in any of these. I've done all my summation here. That's my summation. And it's easy because I've chosen local inertial frames in which everything's easy. Everything's easy. So there it is. Let me write it out in what is this term? This is equal to R alpha beta mu nu. And that's equal to this monstrous thing here. Well, I say monstrous. It's a damn sight easier to evaluate this than it was before. It's a nice equation. This is true in a local inertial frame. So here's a black hole. Here's another black hole going to kill it, going to orbit around it, and all sorts of terrible things are happening. And here's me, and I think, oh no, I'm going to die. What's the Riemann Christoffel tensor? Build an elevator on myself. Construct a local inertial frame. And my Riemann Christoffel tensor with 4 downstairs indices is this thing here, which is just 4 variables. Just 4 terms. Okay, well that's nice. Well, the reason it's nice is that I can evaluate it, but I can also play with it. I'm going to derive in subsequent screencasts a whole bunch of symmetry properties of the Riemann Christoffel tensor, which make it a lot easier to consider the Einstein field equations, which I'm gradually working up to. It's taking me a lot longer than I thought, but this is relativity step by step, and there's a lot of steps. Stop.